is a postdoc at the CS department in CERIAS.
Good afternoon, and thank you, Professor Bertina, for the introduction. Today I will present a paper on private queries in location-based services. This work has been presented earlier this year at the ACM SIGMOD conference in Vancouver. I will first give a brief outline of the talk. So, what will be covered? I will first give a brief overview of privacy in location-based services. Then I will review some of the existing solutions that solve this problem. Most of the solutions will use spatial cloaking, and this is the reason why they have certain limitations, which I will discuss. And then I will move on to present our technique, which is different from existing solutions because it uses cryptography to solve this problem. And more specifically, we use Private Information Retrieval, or PIR. I will try to stop every few slides so we can answer any questions that may arise. And I have also included slide numbers if you want to refer to a particular slide. So moving on to the location-based services, or LBS overview. The users of location-based services have mobile devices, and these devices are GPS enabled. The users are able to ask queries which are relative to their location, for instance, nearest neighbor queries. We have here an example with a number of users shown as dots and a number of points of interest. In this case, we have hospitals age 1 to age 5. In our example, we have user U1 who has the query, find the closest hospital to my present location. This query can be answered in a public location server, for instance, Google Maps, which stores the points of interest. However, the location server is not trusted. And in addition to that, we may have some malicious attacker which intercepts the query from the user to the server, and the attacker can infer that U1, for instance, may suffer from a medical condition. And this is a violation of the user privacy. We want to prevent that. One immediate solution is to have U1 remove his identity from the query. So instead of sending the exact identity of the user will use a pseudonym service or anonymous web surfing service. There are a lot of those services nowadays. But there is still a problem. In order to process the query and return a meaningful result, the query must contain the location of the user. And this location can be mapped to the user identity, for instance, using signal triangulation, or even with more simple methods. If, for instance, the user issues this query from its residence, then it is very simple to look for this address in a public telephone directory and we can find out who the user was. So the problem that we're trying to solve is how can we still provide these location-based services, and at the same time we want to preserve the anonymity of the query source. And there are a number of techniques that have been proposed so far. Most of them rely on the Spatial K-Anonymity concept. K-anonymity is a concept borrowed from relational databases. And the idea is that the query issuer is hidden among other K-1 users. And therefore, the probability of identifying some individual user is bounded above by 1 over K. How can we do this for spatial K-anonymity? The idea is to build a cloaking region, or an ASR we call it, an anonymizing spatial region, which will enclose the location of at least K users. So revisiting our example, again we have U1 asking the same query. It's just that this time, instead of sending the exact location of the user to the server, first there is this rectangle, this ASR which is built. In this case, we consider the value of parameter K to be equals to 3. And we have a 3 ASR. The server will process the query with respect to this ASR. And because of that, a number of redundant results will be included in the response. Why? Because in addition to H2, which is the actual answer, there are also hospitals H3 and H4, which are candidate or potential nearest neighbors of some point which lies within the region. And enlarging the exact location to a region adds some additional overhead for the query processing. And there is another factor. there may be some financial cost or billing cost associated to this enlargement. Why? Because we can see here that we send 3 times as many results as in the case of the point query. And if the user is billed with the amount, with respect to the amount of the results returned, then this will result in an increase in cost. I will come back to this issue later in the talk when we will compare with existing solutions, and I will discuss more about the financial cost involved. Now that we have an idea of how to achieve anonymity, we see that there are a few elements here. We need, for instance, to know the location of other users. So how can we enforce this privacy paradigm? Most solutions use this architecture. It's a 3-tier architecture. On the left-hand side, we have the users with mobile devices. On the right-hand side, we have the location server. In the middle, we have the anonymizer service. I will just refer to this as anonymizer so we don't confuse it with the location server. What happens is that users will subscribe to this anonymizer service. And then each user has to periodically update the location where he's situated. Whenever a query is sent, instead of sending the query directly to the location server, we will send it first to the anonymizer. The anonymizer will assemble the ASR, as we have seen in the previous example. Then the ASR is sent to the location server. The location server will process the query, send back the candidate results, which, as I mentioned earlier, are a superset of the actual result. And then the anonymizer will filter the result and send back the actual result to the user. There are a few obvious flaws with this architecture. First of all, we have a single point of attack. If somebody breaks into the anonymizer, everybody's privacy is compromised. And another problem is a performance problem, because all the queries and all the updates of locations must go through this server. Therefore, there would be a performance problem, right? A bottleneck. I will now move on to discuss specifically, so we have seen the architecture that is used, and I will discuss specifically a few methods, and we will only look at the part which happens at the anonymizer. So we want to know exactly how the ASRs are built. The first paper that I'm going to introduce is Casper, the first method. This is a VLDB 206 paper. The idea is to store all the user locations in a spatial index. In this case, a quadtree index is used. The quadtree is a very simple spatial structure which partitions the space into 4 quarters, 4 quadrants. And this is recursively performed until some condition is met. For instance, every quadrant contains at most 1 user, or some other number of users which fit in a disk page. How is anonymization performed? Whenever a query arrives at the anonymizer, the algorithm will search for the lowest level quadrant in the tree, which contains the query source, as well as k-1 other users. So this is performed in a bottom-up fashion. And let's see an example. Again, let's assume k equals to 3. And maybe let's assume that u1 or any of u1, u2, or u3 issues a query. According to the algorithm that we have just described, the solution will be, or the cloaked region obtained will be A1, the red rectangle. Now, if a query is issued by u4 with the same parameter k, we will obtain the A2 region, which is obviously larger. Now, if an attacker has some knowledge on the distribution of locations, so he doesn't even need to know the exact locations. All we need to know as an attacker is the distribution of locations. Then, by simply looking at the size of the generated ASR, the attacker might see that U4 must have been the query source, right? So this method exposes the privacy of the outliers. How can we deal with this? After Casper, there was another method proposed which talked about the concept of reciprocity. This is actually also our paper. It's a TKD 207 paper. So this property, which in retrospect seems pretty simple, says that whenever some user UI generates an ASR, and that ASR includes some user UJ, then the reciprocal must occur. Here in this example, whenever U2, U3, or U5 issue a query, we will have the associated ASR. And similarly, whenever U1, U4, or U6 issue a query, a different ASR.